Okay, so I'm actually going to show you a video now about successive ionization energies. But what I want you to notice before I show you the video is that when we start also removing electrons from very stable configurations, we see a dramatic increase in the ionization energy. So if we look at this slide here, when we remove one electron from magnesium, so we're forming Mg plus 1, we need about 736 kilojoules. We remove the second electron, we see about a 2 times increase, form Mg plus 2. We remove a third electron. Now we're starting to remove some of those core electrons from a very stable configuration of a noble gas. Now it's about 7 times increase to form Mg plus 3. We see something similar with aluminum. Here, removing the first electron takes about 577 kilojoules, thus forms Al plus 1. Moving a second electron, we have about a 3 times increase. This is Al plus 2. Moving a third, it's about a 2 times increase. This is Al plus 3. Remove a fourth. This is about a 5 times increase. This is Al plus 4. So here we see the largest jump with the ionization energy. We remove that core electron once again from a very stable noble gas configuration. So like I said, I want you now to watch a video which will show you in more detail about these large jumps in the successive ionization energy and how you can use that to identify which element or which group the element might be in.
To successive ionization energies and their patterns. Many elements need to lose electrons to become stable, but electrons are held to the atom by the attractive force of the nucleus. Positive and negative charges attract each other, so energy is required to remove an electron from that attractive force. That energy is called ionization energy, or IE, because removing an electron creates a charged atom, which is called an ion. The unit for ionization energy is kilojoules per mole, which refers to the amount of energy required to remove 1 mole of electrons from 1 mole of atoms. Given this definition, does the unit kilojoules per mole make sense? Let's begin by taking a look at energies required to remove electrons from magnesium. The electron configuration is shown at top right, and we are keeping track of the ionization energy in the graph at bottom right. And we see that neutral magnesium has 12 protons and 12 electrons. Note that magnesium wants to lose its 2 valence electrons to acquire the stable electron configuration of neon. The first ionization energy is relatively low, as shown on the graph. Now, however, with 1 less electron, there is more attractive force per electron from the same 12 protons. How will that change the amount of energy needed to remove the second electron? Got it. Yes, you're right. It is harder to remove the second electron. It requires more energy. Notice that magnesium is now a 2+ ion and has reached a stable neon configuration, with even more attractive force per electron. But other relevant changes have occurred as well. Shielding is greatly reduced from 10 to 2, so effective nuclear attraction, or ZEF, significantly increases the attractive force on the current outer electrons. And it has reached a stable noble gas configuration. What will all of that do to the amount of energy required to remove the third electron? Got it. Yes, that's right. It takes a lot more energy. These are called successive ionization energies. The first ionization energy, or first IE, is the energy required to remove the first electron. The second IE is the energy required to remove the second electron, and so on. So these are successive ionization energies, or successive IEs. What patterns can we see when looking at successive ionization energies in adjacent elements? Let's compare the successive IEs of sodium, magnesium, aluminum, and silicon. First, and very importantly, we need to make sure we are acquainted with where valence and core electrons are on our atomic model. It is the outer energy level where the valence electrons are, and it is the inner energy levels where the core or inner electrons are. Note that with these four elements, the core electrons represent the stable noble gas configuration of neon. Also important, notice that each succeeding element has one more proton, which increases the attraction the nucleus has for their electrons. And now we can compare their successive ionization energies. Let's keep track of each successive ionization energy on a vertical axis at left. The first ionization energy of sodium is low, but that gets us to a neon configuration. So will there be a large change with the second IE? Yes. Sodium's second ionization energy is nearly 10 times that of its first IE. How does that compare with magnesium? We know the first and second ionization energies are low, but the third, now removing an electron from a neon configuration, is much higher. Can you see what the pattern will be with aluminum and silicon? What will happen to their ionization energies once they have lost enough electrons to get to a noble gas electron configuration? For aluminum, the first, second, and third IEs are relatively low. Those three ionization energies have removed all the valence electrons. The fourth IE removes an electron from the core electrons, a neon configuration requiring a big jump in energy. For silicon, we see a similar pattern. Now removing the fourth valence electron gets us to a neon configuration. What's going to happen with the fifth ionization energy? You're right! A big jump for the fifth ionization energy, which takes from a noble gas electron configuration. If we compare the successive ionization energies in a table with ionization energies for valence electrons in yellow and core ionization energies in orange, we can see the big jumps in ionization energies for each element occurs at the point when removing an electron from a noble gas electron configuration. Sodium loses one valence electron to get to the 10 electrons of the neon configuration, so there is a big jump at the second IE. Magnesium loses 2 electrons to become stable, so the big jump is at the third IE. Aluminum loses 3 electrons to have a neon configuration, and so the big jump is at the fourth IE. And silicon loses 4 electrons to get to the core, and so its big jump is at the fifth ionization energy. What do you think the pattern would be for elements in other periods? Notice that the amount of electrons removed before a large change in ionization energy is simply equal to the number of valence electrons for that element, and so identifies the group of that element. Elements with 1 electron removed before a large ionization energy change all have 1 valence electron and so are in group 1. Elements with 2 electrons removed before a large ionization energy change all have 2 valence electrons, and so on. You should be able to determine where the large ionization energy change will occur for any element in groups 1, 2, and 13 through 18 based on their number of valence electrons. Note that we have only dealt with ionization energies of main group or representative elements. Because transition metals are filling d orbitals and can lose more than one specific amount of electrons to become stable, their successive IE patterns are more obscure. That's it for today's Mad Scientist production.
Okay, so what we're going to do now is I want you guys to practice this. So I want you to look at a table of ionization energies and try to predict which elements that they might be talking about or which period they might be talking about. So in this example here, it says that these are for ionization energies for elements in the third period. So I want you to label each box with the correct element. So why don't you pause this, try out those problems, and then start it again, and we're going to go over the answers. Okay, so let's go over these. So when I do these kind of problems, what I think about is like how big of a jump we have each time. So if I look at 496 to 4560, I see that's a jump a little bit less than, sorry about that. I see it's jump a little less than 10 times. If I look at the next one, this is a jump of less than 2 times. I look at the next one, this is a jump also of less than 2 times. So I'm seeing the first jump is the largest of those two. So what I do is I remember that before I see that large jump, I'm removing the last valence electron. Okay, so this means this first row here, this element only has one valence electrons. Okay, so let's do the next one. This jump is about 2 times. This jump is about maybe a little less than 6 times. And this jump is less than 2 times. So I see that the largest jump is from the second to the third. So this tells me this one has 2 valence electrons. Okay, let's do the next one. This jump is about 3 times. This jump is about 2 times. And this jump is about 5 times. I see this time the largest jump is from the third to the fourth ionization energy. So this tells me this one has 3 valence electrons. So again, I'm always focusing on where that large jump is. And that tells me that the electron that was removed prior to that large jump was our valence electron. Okay, so this tells me that the first element, since we're in the third period, that the first element would have to be sodium. The second element would have to be magnesium. And the third element would have to be aluminum. But I only know that because it tells us we're in the third period. Okay, so let's do another one. Okay, so I want you to try this one, and then we're going to go over the answer. So pause this. Okay, so again, I want to look at how large a jump we have each time and see where I have the largest jump. So here, I look at the first one. From the first to the second is a jump of about 2 times. From the second to the third is a jump of greater than 5 times. So the largest jump is from the second to the third. This tells me that this element has 2 valence electrons. So again, I look where the largest jump is. The electron prior to that, it means it's 2 valence electrons. I know this has to be group 2, and therefore I know it has to be a member of the alkaline earth metal since it's in group 2. Okay, so let's try another one. I want you to look at these, and all you're figuring out here is which group this would be likely to found in. Okay, so try these out, and then we're going to go over the answer in just a minute, so pause the screencast. Okay, so let's go over this. So first jump would be about 3 times. Actually, excuse me, that's going to be about 2 times. The second jump will also be about 2 times. Third jump is less than 2 times. Fourth jump is about 4 times. Fifth jump is less than 2 times. Okay, so largest jump here would be this fourth jump. This means that this will be our last valence electron. This would have to be a member of group 14 because that's 4 valence electrons. Okay. And the reason why I'm saying that is typically we don't really consider the d electrons as valence electrons. So I'm just focusing on s and p valence electrons. Okay, so if you have questions about this process, please feel free to email me.